I joined Search Technologies, which was started up by a bunch of my friends, and we've been growing that company. One of them who's right back there. Hey, John. We've been growing that company since 2006. It's just been fantastically successful. We're now over 100 people. We're operating in something like countries all over the world. We have some 400 plus customers. It's just going really, really well. When I started with Search Technologies, we really hadn't done anything with Lucene and Solr. And so I was one of the ones who said, you know, this is going to be a big thing. Let's really get into it. And that was around 2008, maybe, 2007, 2008. And so we dove headfirst into Lucene and Solr. And now it's, I would say, probably responsible for about half our business. And so it's just been, you know, really wonderful. And being a search engine junkie, and I mean that in a truly negative, addictive way, as in it impinges on my life in ways that it shouldn't. So being a true search engine junkie, you know, I just love Lucene and Solr because I can plug anything I feel like into it and make it do anything I want it to do, and make it dance, right, and make the application sing. And that's kind of what we're talking about, is making search engines dance and sing. And that's kind of what I wanted to get about with this whole presentation on query parsing. Was because the, you know, I don't think we're there yet on the query side. I don't think we're there yet on the indexing side either. And so, you know, one of the things that Search Technologies is spending a lot of time at is looking at how we get things into the system and how we do searches, and approaching those different areas in terms of adding flexibility, making things really sing, making applications that really elevate us beyond the simple flat list of search results and off-the-shelf relevancy into something that's really specialized for the particular content that you're searching for. And that's another big kind of main message point. Like, and if we have the big network graph like we saw from the LinkedIn guy, one of the big items would be data. We have a reverence for data. And I mean that in an almost religious, you know, aspect. We really believe that the data is king and that the data is something that you should revere, not try and fit into a common box, but let the data be what it is and try and extract everything you can from the data. And so to that extent, you know, we believe that every application has its unique data, has its unique pluses and minuses. A library cannot be searched in the same way as a web page. You know, a web page cannot be searched the same way as a curriculum vitae, and so on and so forth. And so all those aspects. I hope I can just press down. OK, cool. Well, we haven't tested this on Macintosh, so cross your fingers that all the animations work the way they're supposed to. And so I've already covered all of this, basically. That's Search Technologies. We also have a booth out there, so I'll be hanging around there if you want to chat. OK, so let's just talk a little bit about Lucene relevancy. And this is more in the realm of background. Lucene relevancy is based on pretty simple mathematics. Now, just the fact that we have the multiply operator is a big step forward. A lot of the search engines that I've worked with in the past, I think I can say, right, because they're no longer a real search engine, but the fast search engine, for example, had only add. It never had multiply. So the fact that we have multiply is a big step forward. Basically, the way that Lucene relevancy works, right, is that you construct this query tree, and the numbers bubble up to the top, and that gives you the number for the document as a whole. So for every individual term, you can compute the score for that term using the TF-IDF of the term, and that's implemented with the default similarity class and the term query class, where the TF by default is the square root of the number of occurrences of that term in the document, right? And the IDF is an idea of how valuable that term is to the collection as a whole. So terms that occur very infrequently are said to be more valuable. Terms that occur very frequently, like, you know, small function words, tend to be less valuable. They throw in a logarithm to make sure it doesn't kind of overwhelm the numbers, and, you know, they divide it by the total documents in the collection to make sure you get reasonably scaled numbers, and they do some adds. And the whole point is that this is completely ad hoc, with no actual, statistical or mathematical foundation other than somebody thought it was a good idea. Okay, so I mean, fundamentally, just saying TF-IDF, pretty much an ad hoc algorithm, but that's okay. Let's not worry about that too much. Let's just go on. Okay, so now we have these larger search expressions. So, that's the score for a single term. How do we get about doing the score for a larger query? Well, if you have an AND, you just take the score of the term A and multiply it by the score of the term B, and that's the value for A and B. So very easy. If you have an OR, you just take the score for term A and you add it to the score of term B, and that's the score of the thing. So these are implemented with Boolean query. And then there's disjunction max query, and that says, well, take either the maximum of term A or the maximum of B, and whichever one is the maximum gives you the score of the whole thing. So we put this together. Here's a simple query, probably not a very realistic query. We're trying to find George Martha Washington or Custis. Martha Custis, anybody know? Is Martha Washington's maiden name. So supposing that these are the numbers, these are probably all way too high, but supposing that these are the actual score numbers for the terms, now we can bubble those up and say, okay, our document has George and Martha and Custis in it. So that's what the check marks mean. For a particular document, we find all the entries that have that. We bubble that up and we say, okay, the max of Washington and Custis is 0.9, so the max is 0.9. The OR of George and Martha is 0.1 plus 0.2, so that's 0.3. And then you bubble that up to the AND, which is 0.3 times 0.9. That gives you 0.25. Pretty basic. So far, so good? Okay, so what we're constructing is formulas for computing the relevancy of the score with add and plus, basically. But fortunately, that's not all that we have available to us. We have other things that we can use. Less used, but incredibly powerful if you can use them and know how to use them. Like boost. You can just set the boost for anything, the boost of any operator or the boost of any term, using just query set boost. And all it does is it takes the value of the item and multiplies it by the number. So you typically multiply it by things like 2 or 1.5 or 0.5 to either increase or decrease the value of that item to the formula as a whole. A constant, if A, then set it to the value f. Otherwise, set it to 0. So that says, if I have A at all, ignoring what the score of A is, now we're just going to set it to the constant value f. That's the constant score query class. Boost plus. This is my favorite because it's subtle. And this is a subtle thing you can do with Boolean query, which a lot of people don't realize. If A, then A plus B, else 0. So that's interesting. You have essentially a required item, that's A, and then you have optional items that are B. If the optional items occur, they increase the boost of the item. If the optional items don't occur, they decrease. It's just A. So it's a very interesting thing of making sure you always get A, but then you can kind of tweak the relevancy scorings as to whether they have B or not. And that's just with Boolean query with required clauses and optional clauses. Shoulds and musts, I guess, in the parlance of Lucene. Boost mul, this is a boosting query, less well used, but I like it a lot. If B, then you multiply A times F, else A. So that's kind of cool too. So you can say, if I have, all the documents have to have A, but in addition, if they have B, then I'm going to multiply it by some factor. If they don't, then I won't. Oftentimes this factor is less than 1, so that I can have a negative boost. So all the documents which have this thing are pushed down. All this, so that's essentially the boost mul. Okay, so now we get to the kind of the problem is, basically there's a big need for more flexibility, and this is part of the evangelism aspect. There's a certain thinking that pervades this community, and I want to kind of lift that thinking up into a different type of thinking, and that's where I'm going to be proposing scripting and things like that, and domain-specific languages for constructing queries, which I think will move our industry into a whole new realm. And so we'll talk about that in a little second. The issue is with flexibility. We do most of our work in these weird query expressions with curly braces and bangs. We do most of our work with analyzer chains, pipelines and things like that. And it was Christmas. I don't know why I always remember that it was Christmas. But at some point I was like, you know, pipelines are really not the right way to construct hierarchical queries. A pipeline is a linear thing. A hierarchical query is this hierarchical thing. Wouldn't it be better to have hierarchical traversals and things like that? Then I'm like, well, what the heck is the best way? And then I'm like, oh, it's functional queries. You know, if you did a functional programming language like Haskell or any of those others, you know, wouldn't a functional language be much better at constructing queries than pipelines and all these other things? And I was like, oh my God. Then the neurons start firing, and my wife, who says you're addicted again, she says, come back to the real world. So, you know, we're here. We have this need for flexibility. It's really difficult or impossible to use all these available operators. Lots of them are not available in the standard query parsers. Getting them into the query parsers is really complicated. A lot of people do that with string manipulation. But we saw the strings that you kind of create with all those bangs and curly braces. It's a mess. It's, you know, it's just a mess. You can't really expect real people to construct those weird things. Query construction is in the application layer so much of the time. So we push out. We say, here we have this thing. It does all these things. Here's the documentation. Now you, application programmer, create these queries. But the application programmer's like, what the fuck, you know? So I mean, seriously, are you asking your UI programmer to create query expressions? The answer is everyone does. But should we? No, obviously. Seriously? And you know, it's really hard to create and use new operators because you have to get into the query parsers, and it's a pain. So what I'm going to propose, and what we've done at Search Technologies, is we've created this thing called the query processing language, QPL. It's a query processing language that lives inside of Solr and actually takes the user interface parameters, constructs the actual query expression, and sends it to search. Now, because it's actually server-side inside of Solr, it has complete access to all of the operators you could ever want. So there is no limitation at all in terms of having to translate. And it operates off a QPL script, which is the purpose of taking the user inputs and converting into the query language, which we then send to the search engine. Now, lest you think that I enjoy, you know, writing new programming languages, which, you know, if I admit it, I do. But I didn't in this case. QPL actually lives on top of Groovy. And so it's a series of methods and static classes and other things that turn Groovy into a domain-specific language for constructing queries. So that's this. You can learn all about it on our wiki page. That's public. We have two plugins now, a query parser plugin and a search component plugin. I call it the 4GL for text search query expressions. I'm sure that all of you were born after the word 4GL was invented because you're all so young. But you know, in good old relational database days, we started with SQL Select, and then we wrapped that with PL/SQL, and we called that 4GL. And so this is essentially taking queries and wrapping them with scripts to create something that's way more powerful than just a query. I mean, like insanely more powerful. And it gives us server-side Solr access for cores, analyzers, embedded searches, results XML. It's just, you can do just about anything with it, really. The plugins, we have this query preparation. So these are two search components that you configure as either a query prep or to analyze the results and provide additional data. It also can be plugged in as a query parser. And you can have as many of these as you want, each of them with their own SQL script. So it provides a really, QPL script, each with their own QPL script. So it provides a great level of componentization to the whole thing. Configuration of it is dead easy. Basically, you stick in a new query parser or a new search component. This is the script itself. That's the default search field that would be used for ordinary tokenization and things like that. Search component, the script, the default field, and then is process script. This says whether the script is run at the prepare stage or at the process stage. So it lets you actually modify query parameters before they get to the actual query engine if you want to do that at the prepare stage. So let's take a look at some examples. First, we tokenize. This is the query string as entered by the user. That's essentially the Q parameter. So we send it to Solr tokenization. That actually runs it through the Solr analysis comes out with a list of terms. So it's just a list of strings, basically, that come out of that. So the end result of this is a list of strings. We then turn that list of strings into a phrase with this phrase operator. We then turn that same list of terms into an AND query. Nice. We then construct the final OR. Oh, sorry, that's not the final one. I added this at the last minute, late last night. I even forgot it just now. We throw in an OR query. Now I wanted to do a kind of more sophisticated OR query, right? So I said if the number of terms is less than or equal to 2, it's just going to be false. Null in this language is false. Otherwise, we're going to use the OR min operator, which is the OR with the minimum number of clauses match. And we're going to say we have to match at least more than half of the total clauses in the system. So if you enter a 4-word query, we'll have to match 3, I think. If you enter, or 2 or 3. If you enter a 12-word query, you have to match at least 6. So that you just don't get those random ORs where just a single thing matches, which is, as we all know, a sign of bad query relevancy scoring. So then we stick it all together. And here we weight the phrase at 3.0. We weight the AND at 2.0, and then we have the OR. So what we've done inside of Groovy is we've overloaded the exclusive OR operator, right, with the weighting. And so you have the phrase operator, we weight that 3.0, the AND operator, weight that 2.0 OR query. That leaves the QPL. It then gets built into actual Lucene query structures and then gets executed by the engine. So it allows you to do all kinds of scripting and testing and just anything that you want to take that original data that came from the user, write it into query expressions that go into Solr. And I can't, it's changed my life. I mean, what's sad about that expression is that it really has. So Thesaurus example number 2, here's where we stick in a thesaurus. We have our own thesaurus expansion capability. You load the thesaurus here. That's done, and it's cached so that if it looks that up again, so every time it re-executes the script, it doesn't have to reload it. The thesaurus expansion is with the thesaurus.expand operator. This is different, right? We're actually setting the expanded terms to 0.8. Why is it that the synonyms, quote unquote synonyms, are always exactly equal to the original term? Do you not really trust what the user actually typed in? Shouldn't you bring out what they actually typed in first and their synonyms later? That's just those little things like that, which I think make an impact on relevancy scoring that make a big difference. So when we take a look at the results, somebody told me that bathroom humor was always funny. So I said, well, let's try bathroom humor. Bathroom humor is our query. So we take the word bathroom, we run it through the thesaurus. This is a completely made-up example. But bathroom, loo, and WC, and then humor, and jokes. So then this might be the sort of thing. This is not the sort of thesaurus expansion I would typically recommend to a customer, But if that's the sort of thing that you want, that's fine. But the point is that the thesaurus expansion doesn't actually, it takes each of the individual terms and expands them and gives you a list of ORs, right? It doesn't actually construct the final query. And so what we have to do then is surround that with an AND operator, and then that becomes the results. And so what we have here in 2 lines of code is thesaurus expansion, and a relatively powerful and useful version of thesaurus expansions as well. Let's talk about some more operators. There's the Boolean query parser, where you pass in an entire query string and out comes a QPL query tree that you can then process and manipulate in other ways. Relevancy ranking operators were mentioned. Remember I mentioned boost plus, boost mul, and constant. Those are actually represented as operators inside of QPL, which correlate directly to those Lucene classes that I had already talked about. And composite queries. So the idea of taking a list of items and then applying them to 2 fields at title and body, title at a 1.5 score, body at an 0.8 score. And so it's kind of a distributive operator which takes each of these, all combinations basically of the list of operands against the list of fields, returns a list of that, which you can then AND together, and then that becomes your resulting query. So this doesn't actually result in any kind of special Lucene operators, just implemented with regular Boolean queries underneath. Okay, so let's take a look at a newsfeed use case. This is a use case that came from an actual customer. This is how they wanted to do relevancy scoring for their system. This was actually 1/3 as large as what they gave us. They actually gave us a list of 27 different levels that they wanted us to implement. And so let's see how we would implement this in QPL. First, we notice that it's divided into 2 ranges, today and yesterday. Oh, I'm actually doing quite well on time, I think. Today and yesterday. And so we have 4 levels in today and 4 levels in yesterday, and then we have older. So what we want to do is, and then we look at all this and let's say, okay, we have a query over markets. We have a query over terms. That's markets, terms. Companies, we have a query over companies. So we have really 4 different types of queries: markets, terms, companies. We have 3 different types of queries: markets, terms, and companies. Right. Okay, and so then everything else is just a combination of those 3 queries. And then we have today and yesterday, which, they want to weight everything that came in today over everything that came yesterday. So we could do this with, function queries perhaps, but, they're kind of slow. It'd be nice to do it with the native relevancy scoring that comes out of Lucene. So the first thing we're going to do is we're going to create those 3 subject-oriented queries I talked about. Now here's a really cool thing. Every single parameter that you send into the URL is automatically available in QPL by just saying dot and then the parameter name. So that means the user interface would just give us a list of markets on the URL. And then we can just fetch that list of markets here. For them, it's a semicolon separated list of markets, right? So we just divide that up into, we split that on semicolon. That gives us a list of markets. We wrap that with or, apply it to the markets field, and we're done. So they just give us the list. The UI programmer doesn't even need to think. They just take those checkboxes, put that in a semicolon separated list, pass that in on the URL. It can't be easier for them. And that's one of the things I'm trying to emphasize is we make the job easy for the UI programmers. We centralize the knowledge of search around the search engine, around the people like you who understand the search engine and understand the index and understand how to write queries. This is the terms query. For them, that was the actual query string. So we just tokenized the query string the way we would. I threw in a Thesaurus expansion just for grins and then applied that to the body field. And so that, in their particular case, they had you enter a list of topics you were interested in looking for. And so that's why we chose the or here. Typically, I would use an and for that. But because in their particular user interface, you filled out the list of topics you wanted to follow. Probably this would be a lot more sophisticated with phrase searches and maybe near scoring and a bunch of other things. But this is a simple example. And then companies and company IDs. In their particular case, when you're following a list of companies, they actually gave you company IDs, not actual company names. And so again, we do the splitting on semicolon, construct the or, apply it to the company IDs, and then we're off and running. Okay, so this is actual QPL, very close to the script that we actually implemented for that customer. Now let's look at the time. Because it's a regular Groovy program, we can just do anything we want because it has full access to Java, right? And so here we are, we're creating a new simple date format. We're using calendar.getInstance. And so now we're getting today's date, right? And applying that to the date field. So now we have a query over today. That's pretty straightforward. Now we want yesterday. Well, we decrement using the calendar by 1. That gets us yesterday. And now we have a query over yesterday. And so, the other cool thing about it being Groovy is that you have everything you will ever want from regular Java to be able to manipulate your queries so that you can just process them. This assumes, of course, that the date is written into a date S, right, which is a string representation of the date. So that's a single token search rather than a date range, which is a lot slower. So this is going to be a ton faster than doing a date range over a regular date field because you're only going to be doing essentially searching for today token and yesterday token and then adding that to the relevancy ranking. So it'll be much, much better performance. OK, so we have all the pieces. Now let's start putting the pieces together. The first part is we're going to put the weighted subject queries. And just because we want it to be 100% perfect, right? We don't want Solar TF-IDF to kind of get in the way. Okay, we're going to be wrapping all of these with constant queries, 4, 3, 2, 1. So that'll take the and of the markets query and the terms query. 3 is just the markets. 2 is just the terms. 1 is just the company IDs. And then we take the maximum of those 4, and that gives us the subject query. So I'll just stop here for a second. And does that make sense? I mean, you compare this right? 1, 2, 3, 4 to that. And you're like, wow, there's a clear correlation there. I could see how that gets put together. The whole point of this is to make it easy to understand and easy to use, and to have a very concise way of constructing these complex query expressions. I see some nods. Have I lost anybody? Make sense? Cool. OK, so we have the subjects. That's 1, 2, 3, 4. Now we're going to do the same thing with the weighted time queries, except we're going to weight this today as 10, yesterday as 1, and we take the maximum of those. So any document, I doubt that a document will ever be tagged as both today and yesterday. Although technically, midnight, exactly midnight. Somebody said, is midnight yesterday or today? And somebody said, it's both. And that just blew my mind. How could midnight be both yesterday and today? So if you published an article that was technically on midnight, perhaps it would have both today and yesterday. In which case, today would dominate because of the max, and you'd end up with 10. You wouldn't end up with anything in the middle. Yeah. Oh, that's a good question. I think if you're looking at time zone differences and things like that, what you might ask the user interface is to provide the time zone of the searcher. Okay? And then you could add that into the calendar here. So if you provide the time zone of the searcher on the query line, see, this is where questions like that just get answered so easily, right? You barely have to write any code. You just add one line. You can just get solar.timezone, add that directly into the simple date query, and then you're shifting your time zones based on what the user wanted. Although I guess that the fact that it's date s, it's stamped on a particular time zone, so that's probably a problem. These searches would have to turn into actual date range searches. Or oh, OK. I see. Yeah. So in that case, as I mentioned, you'd want to turn in the time zone, whether it's DST or whatever, and then you would do that manipulation here. But that's a good point. The queries would have to be range queries instead of to get it perfect based on what the user was looking at. But again, it provides a framework for solving those sorts of problems in a relatively straightforward and obvious way, I think. OK, so now we have the subject query and the time query. And what we're going to do is we're going to AND them together, right? So that means if it's today, it's going to be 40, 30, 20, 10, because the AND is multiply, remember? And then if it's today, it's 1, it's going to be 4, 3, 2, 1. And so it all comes out exactly the way that it should. Oh, I should have printed it out, because you can look at these, and sometimes they're like a half page long. They end up being enormously large. And that's with all the string manipulations that people would typically do on the web application side. This takes care of all that, and all that goes away. It works well enough that we tend not to worry about it. So, but when we do debugging, of course, we look at the full resulting query expression. But I'll add that to my next presentation. OK, so then remember, if we went all the way back, there was this fallback case, which is everything else, markets and companies for older. And so then what we have is we just have the or of markets and companies. And I threw in a 0.01 just to make sure that was at the bottom for sure. Then the results come out. Now, Solr normalizes this, OK? And so what Solr does is actually looks through the resulting query expression, finds the largest number, which is going to be 10, divides everything by 10. So all of my actual scores will be 10, will be divided by 10. So when you look at the numbers, they won't actually be 40, 30, 20, 10. They'll actually be, 4, 3, 2, 1. And so that just to warn you about that. Although I think today you can actually create a custom similarity module, which will take that out, because I think the query normalizer is actually a method now in the similarity module. So I want to explore that. OK. OK. So we have this. It's plugged into Solr. We said, gosh, we're in Solr. Oh, I've got just a couple more minutes. What else could we do? Well, heck, why don't we reach out to Lucene? We're in the search engine. Let's just reach out to Lucene and do a query. So like, oh my God, we can really do that. We're actually in the Solr search engine. We could just get a handle on the searcher itself and send it a query. So that invented this idea of an embedded search, where inside of QPL, you could do a search to build your search. It's like, whoa. OK, so here's an embedded search. You do solr.search. You tell it what core you want to search over. And then you give it the query that you want to send to it and say, get me 50 results. So it's a very very, very minimal type of search, very, very simple. It basically returns just a top docs list or whatever that class is. And then, but once you have it, we can start using fun, groovy things like results star.subject ID. What that does is get it a list. It actually goes through the list, which is the documents, gets the subject ID for that, gets you a list of subject IDs. And you wrap that with OR, and that gets you the subjects, right? Now, it turns out we do a lot of work with directories, like Yellow Pages. And a lot of directories have one core, which is their taxonomy, right, their subject hierarchy, and another core, which is locations. So they do like a ton of embedded searches. One of our directories customer must do, 7 embedded searches to build the final query, because they're constantly searching over one core to get a list of subjects and then adding that into another core and so on and so forth. So here we're doing a embedded search over one core, adding the results of that, and we put it all together. And so we do take that subjects query here, weight that down a little bit, and the Q with the title, and that gives us our final query. So just embedded search, just basically 2 lines of code. A second example, I'm going to start going through these quickly since I hear other people applauding. So embedded search over categories. This is where we can actually take the results of an embedded search and write it out to the results XML. You can only do this in the Solr search component. And so we're creating a Solr new list. We're adding related categories. We're taking all the results from that categories table and adding up a list of those titles. And then we can write those to the XML response, solr.addResponse, my list. So you enter it. It does an embedded search. The results of that embedded search actually come out in the XML. So rather than using it as a search, it actually just spits out of the engine. Because a lot of us have things like related queries and other things, and this is a great way to do related queries. Other features, embedded grouping queries. Yes, we did it. OK. Proximity operators are query parser, handles adjacent, near, and before. It's the full, and then gives you the full regular query expression. Reverse lemmatization. And the transformer, this is something I wished I'd had a little more time to touch on. It actually does a hierarchical traversal of your query trees and then can swap out operators with modifications. So it's a great way to take this query structure which you've built and then say, for example, anything that's separated by a dash, turn that into a phrase. And you can just apply that to everything, swap out all those dashes to phrases, and do fancy query operations like that. And then the last slide, I just wanted to emphasize that with this, the data is entered by the user, and then the Boolean query expression goes into the search expression. And what that means is that the application development team can do what they know best and provide the widgets and the widget output in exactly the way that they want. And then the search team can be responsible for actually turning that into a strongly relevancy ranked query. So it provides a separation of organizational responsibility, which I think is critical, which relational databases have known about all this time. And now we're applying to search as well. And then that's it, really. Thanks very much. In terms of large distributed systems, I think there's a question of what level of accuracy that you need to have in terms of applying synonyms and things like that. Ultimately, you come back with a relevancy rank list of documents from everybody, and you're merging them together. And so the question is, do you need to go out and construct all the different synonyms and then construct the final query and then send it out again with the two-phase, which I know that Solr does for a lot of situations, like grouping, I know is like a two-phase process. So I guess to say that I haven't looked into it. Most of our customers are small enough that they live within a single Solr server. That's where this was developed. We have not integrated this with distributed. One of our customers is using it in distributed search, but not for scenarios like that. So I'd have to do a little more research.